this is before lunch, so I appreciate your time and like willingness to sit in this room. This topic is not like I put cloud native. I know this is all about Kubernetes and how you deploy systems and infrastructure-oriented conference, but I still thought I'd submit this because at the end of the day, we're all building distributed systems, and how it's also important to know how to build these, and also maintenance is a paid scalability and all that. Those are great, but fundamentally, how you build systems is also important, right? So that's why I thought I'll submit the talk. And yeah, this is mostly about how you write software and how you build things that are fundamentally very important. If you don't consider these design principles, systems will eventually they'll be slated to fail. Yeah, that's why this topic. So I wanted to discuss the challenges of building distributed systems and the importance of incorporating idempotency into building reliable, distributed, consistent systems. So along the way, I'll talk a bit about temporal.io. Some of you might have heard about that. It's an open source. It's an open source workflow orchestration engine that will help you build all those reliable, scalable, consistent systems. Yeah, so the topic is about why idempotency is important in building software systems. A bit about myself. I am from India. I live in the Silicon Valley. I've been living there for 15 years. I used to be a software engineer at those companies, and then I found a passion in being customer advocate, being customer facing. So I've moved into solution architecture, post-sales, professional services roles over the years. So I worked at all those open source backed companies. I've only worked for open source projects so far, so yeah, that has been my life's work. And if you want to follow me, that's my Twitter. So if you rewind back to your undergrad days and when you learned about mathematical problems and how those were foundational for building software systems, right? As engineers, you probably want to make sure that when server client setup, this client is sending requests to servers, and you want to make sure that the request to the server is only executed once, even though you're sending the similar request to the server multiple times. That's basically idempotency. You want the end result to be the same, irrespective of how many times you give the request. Meaning, you want the property like idempotency. Idempotence is a property that derived from mathematical terms that applies that. I'm reading from the slide. When you apply an operation once or multiple times, it will give the same intended result. That's the basis for the whole idea of making systems idempotent. It's very crucial because there are elements and tenets of any distributed system. You want like Kubernetes-based deployments, right? You want consistency in data. You want to make sure that systems are reliable, and that in the face of disaster, they are fault tolerant, and all those like retry mechanisms are inbuilt and not really, the developer has not have to worry about keeping the lights on and thinking about how to solve for those edge cases when disaster strikes. And caching, of course, is like a second nature for any system architect. They put caching in their mind when they design. So idempotency goes hand in hand with all these core tenets of software system. The primary reason I say idempotency is crucial is because you have multiple requests that are coming in. You want to make sure these systems, disparate systems, are in sync with data that's coming in, going out, and like the systems are in a when you have two-phase commits and all those kinds of transactional things going on, you want to be able to have a safety net by allowing you to retry an action without worrying about what will cause a data inconsistency. So that's why you want to make sure that the fundamental API, what's writing data, is idempotent. And then you want to make sure systems are fault tolerant. Like software systems are great until they are not, so they'll fail inevitably at some point, and you want to make sure that they don't crash, networks are unreliable, and all those kinds of edge cases. You want to make sure that when all these occur, that an idempotent operation will be in place, and then it will retry without any adverse consequences, like costing the end user experience. And safe retry mechanisms, meaning you want to simplify error handling. One of the ways developers do that is by introducing retries and exception handling native to the code. So this idempotency via durable execution engines like Temporal will do it out of the box for you, and they're also native to the programming language you're doing. So you don't have to learn something new, some new construct or programming dynamic outside of the ecosystem that you're already writing the code in. And caching also aligns with idempotency, because if you want an operation to be, that will be performed multiple times, you want that to be cached without worrying about the data becoming stale or you thinking that the operation will be executed again. This engine will guarantee that only once the operation is executed. So in a world where idempotency doesn't exist, like for example, if you send a record with order ID 1, 2, 3, 4, like in a non-idempotent processing world, the order will be processed twice. And that's not the intended result, right? So if you want to get the desired result, you want to make the system idempotent by introducing some form of logic handling mechanism where you're processing the duplicate orders and then reject the already existing record. The databases do that out of the box, but when you're dealing with the code, you want to make sure that you incorporate these foundational elements. And I want to give you a real-life example of why idempotency is important, or how to draw parallels between real life and software engineering idempotency. A simple example is this stop button in a media player that we used to have in the olden days. You tap the stop button and the player will stop playing, right? And if you tap it again, the player will still stop. Like if you push the stop button multiple times, it will still be in the stop state. It won't play again. That's how the old school players were, and they were idempotent. Just to give an example, even if you hit it 100 times, you'll still be in a stop state. As opposed to, if you compare this to a play pause button in your stop Spotify or other media player apps, you start and then you tap the button. That's the same button for stop and start. It'll when you tap it once, it'll stop. When you tap it again, it'll start. So inherently, this is not an idempotent system. So yeah, the pause and play button, it won't result in the same output, even though you're doing the same operation multiple times. Another example is unlocking or locking your car. You got out of your car, you locked that, and you accidentally pressed the lock button multiple times. It will still be locked. It won't unlock, or any other outcome won't happen. So that's an example of idempotent operation in real life. So there are also real world cases, like in production you'll see APIs, all kinds of distributed system mechanisms like public subscribe, the SOA based architectures, right? You want to make sure that the APIs are idempotent, meaning in order to avoid duplicate messages. Now there's an argument, there are several arguments here. There's compromise of performance when you are striving for idempotency or exactly once semantics. So, but if you want to make sure that the message is only sent once and there's no duplication, inherently developers make sure that they put an element of idempotency by making their producers idempotent, making the acknowledgements only once, and then retries as 0, and multiple ways to do it. I'm just trying to tell that there is this element baked into system, but not often talked about. But it's very important if you're building an app from scratch. Traditional event-driven architectures are great until things become complex, when queues start to fail, and when you also have multiple systems in the ecosystem where you have to keep all of them in the same same page, you'll have issues, right? If without the existence of an orchestration engine or and something that keeps check of all these multiple data points in a pipeline. The goal of developers is to just obviously don't want to spend too much time on these error handling retry mechanisms, but they want to focus on core building apps. So yeah, there has to be a mechanism to decrease this complexity and improve the developer velocity. Those are marketing terms, but I'm just trying to tell you that you have to just, developers don't want to worry about all these kinds of things, but they want to focus on app logic building. So yeah, there is this temporal.io that I ran into, and I had a privilege of working for this company. So they are in this durable execution space. You can think of it as AWS Conductor, but more advanced with more features. It's open source, you can try it today. So it will simplify your app development and make sure that you are delivering your features in less possible time. So what is durable execution? So idempotency is a core tenet of durable execution. So I want to spend a little bit of time helping just breeze through of what durable execution means. Meaning that you are building systems that with an assumption that they'll never fail, or always positive result. Single positive result is your outcome, and you don't want the developers to be distracted by complex plumbing and error logic handling. So that's what durable execution means. It'll exist and execute forever without, wouldn't it be nice to have something like that? That's the goal of temporal IO. They are investing a lot of time in making this more available to many customers out there. So if you take a simple money transfer app, right, this is from the company's GitHub. They talk about how it's a very simple workflow where you send money, and then there are two lines of code where you withdraw money from your account and you send deposit into the new account. So the first step went through, everything looks great, and then suddenly when you're at this deposit phase, let's say the system crashes, and then the state is sort of hanging in there. We don't know what happened. Did it happen? Did the transaction go through? Or what was meant to happen was just even though there's an interruption, the end user shouldn't see the delay or any kind of discrepancy in transaction. So the complete state of this function, including the variables, threads, and blocking functions, there should be a program that should rehydrate the state to the place where it was when the system comes back to normal state. So that's what the temporal does that for you. It will act as a gateway and then carry forward the state to the new server, which is going to pick up the execution of this code. Yeah, so that's what temporal is helping with. It's a very, very beautiful programming model. The platform is doing that out of the box. You can, the temporal supports a lot of programming languages out of the box, like Java, Python, Go, PHP, and many more. They'll help you save the state of the app, and it'll natively do the retries, meaning you don't have to code for it. The system will take care of it. And then the timeouts that you normally have to configure in systems like Kafka, they're all automatically handled by temporal. And you can also schedule code to run at a certain point. You can eliminate the human in the loop things that usually HR and other inventory management systems have. You can bypass all of that complexity using temporal. So how does that work? It's very simple. It'll all start with your language, the SDK that you want to create the workflow in. Basically, you're writing a code, you're compartmentalizing the code into workflows and activities. And your workflow will be your business logic, the activities will be your functions that you want to execute within that workflow. And yeah, the end-to-end workflow will act as a starting point, and then you hop between these activities and you execute the task that you want to complete. There's also a concept of determinism, meaning let's say you change code in the middle of executing something and you want things to happen the same way that happened before. You can make it deterministic by following certain execution semantics that temporal provides out of the box, so that for a given input there is like a defined output and you'll get the same. Even if the determinism is not met, it'll retry until the code will retry infinitely until you go back to the deterministic state. Yeah, the developers can code accordingly. They're out of the box, so you don't have to learn anything new. If you are native Java developer, you can focus on that. SDK libraries are just built in, so there's no additional learning curve. The way it works is you deploy a worker that will run the application, and it plays a very crucial role in automating this whole capturing the state of execution, and it'll run in your environment, and it requires no change in the way you build or deliver code, but you just need to use the temporal SDK. It's other than the normal SDKs you use. Yeah, it captures the state and it sends to the temporal server, which will continuously poll the server tasks until it needs to execute. And the state is stored in databases, and it's a long list of tasks that the task queue handles. And then there are timers and retry policies that gets queued and then executed in a first come first serve manner. There are also algorithms you can configure to make sure that worker knows the state and distributes the tasks accordingly to the appropriate workers. Yeah, all the heavy lifting will be done by temporal server. You don't have to run anything. So yeah, that's basically how it's done on a high level. And with temporal, how do you make sure idempotency is met is that, so this platform captures the complete state of the function, which includes variables and threads and all the functions I mentioned. So you'll just simply migrate the program to another server when things go wrong. In order to do that, the server will call a method repeatedly, and the same result will come every single time, even though there's a new server that's handling the request. And then there are activities you can write. These are basically functions in order to make sure that the systems are idempotent. By leveraging something like idempotent key, it's a familiar concept. You can apply the same concept from database idempotence keys in the code as well, in this SDK-based code as well. Yeah, the key is a combination of request ID and a resource ID in that particular case, and then you'll extract the identifier that needs to be used based on the application you're doing. You could use these combination of keys as idempotent keys, and then make sure that the API or the operation, whichever the API is handling, is idempotent. Yeah, so there are, like, it's a little closer look at how can you guarantee at least once and at most once, and all these semantics that will basically mean you're doing idempotency. Thank you so much for your time. I appreciate your any questions?
You mentioned things like temporal, which is awesome. What about architecture patterns like event sourcing or other popular ways to achieve idempotency?
Basically, yeah, other workflow orchestration engines are also doing idempotency. I'm not aware of how they actually, the semantics of it, but in temporal we do that with activities and workflows. I'm not aware of other platforms or how they do it.
All right, any other questions?
I'm also learning. It's been only 4 months. I've ran into this concept of durable execution. I found it interesting, so thank you.